So first I will be covering the name game. So I will tell the problem first. Suppose you are given n piles. The first pile has A1 numbers, the second pile has A2 numbers, the third pile has A3 and so on till An. Now there are two players, let's say Alice and Bob. So in each player's move, they can pick a pile with non-zero uh, coins in it, and they can remove some number out of them. So if there are y coins, you can, with y greater than 0, you can take some number x and change y to y minus x. Now if all the piles are empty and have 0 coins, you lose. So the players play alternatively with Alice going first. We have to determine which of the players has a winning strategy such that they can always win the game. So have you all heard of this problem before? So is the problem statement clear to everyone? Okay. So now I will explain a solution for it. We will look at the XOR of, and I will also show why it works with the construction. XOR of A1, A2, and so on till An. I will also explain what the XOR operation does. So we write each number in binary. Say this is A1, then this is A2, and so on. And we do this for all the numbers. So now if a particular column has an odd number of ones, it will be a 1. If there are, so this has, say, one more here. So 3 are odd, so it will be 1. This has no ones, it is even, so this will be 0. So this is how the XOR is calculated. You see the number of bits which are 1. Number of numbers which have the ith bit 1. So you see the parity. So does everyone know what the XOR operation does? Okay. So you write each number in binary. Say this is the jth bit, this is the 0th bit, and so on. So now what the how the XOR operation is defined is 1 XOR 0 equal to 1, 0 XOR 0 equal to 0, 1 XOR 1 equal to 0. And also this is a commutative and associative thing. So now notice that the XOR is 1 only if the two numbers are different. 0 XOR 1 is also 1. So what you can do is you can just take the sum of the bits, the value of the jth bit in all the numbers, and take it mod 2. So if these are the values of the jth bit, this is 4, so 4 mod 2 is 0. So the jth bit will be 0. If say there are 3 ones and 2 zeros, the sum will be 3 mod 2 equal to 1. So I will just give an example. Suppose there are three numbers with these. So now the sum of this is 2. So the value mod 2 will be 0. The value here will be 1. The value here will also be 1 as sum is 3. So did you all get the part? This is the binary representation of the numbers. Okay. So now I will claim that the answer of whether Alice has a winning strategy or Bob has a winning strategy depends on the XOR of A1 to N. Now notice if that all piles are empty, AI equal to 0 for all I, then the XOR value will be 0 clearly. So now the claim is if A1 XOR A2 XOR A3 and so on XOR An equal to 0, Bob has a winning strategy. Else Alice has. So now notice that if a1, XOR a2, XOR a3, and so on is equal to 0, suppose this is 0, then notice that after every move we change a number ai to a number less than ai, to j, with j less than ai. And now notice that x XOR, there are two ways of writing XOR. You can use this. This is like the symbol used in codes, and this is the symbol used generally for XOR. So you can use either one of them. So now notice that XOR x equal to 0. And now if you replace AI with J, so the rest numbers remain same. So you can just take it as x XOR AI equal to 0. And now you replace it with x XOR J. Now notice that x XOR ai equal to 0, so x equal to ai. And now you have x XOR j, so ai XOR j. Now these are two different numbers, so they must differ in one bit. So ai XOR j, this will be the XOR value of after the move, with j not equal to ai. They must differ in at least one bit, so the XOR will be 1 in for that bit and the number will be non-zero. So this means from a zero state, we can always go to a non-zero state. We will always go to a non-zero state. Is this part clear to everyone? No. So like I told that you can do moves on the piles. So in each move you take some coins from one pile and remove it. So J is the number of coins after the move in that particular pile. If you choose the ith pile, AI is the original number of coins, J is the final number of coins, and J is strictly less than AI. Okay, so did everyone get that from a zero state you always go to a non-zero state? If you have any doubts, you can ask. So now we showed, like if the claim is true that zero is a losing state and non-zero state is winning, we have showed that from a losing state we only go to a winning state. And now if we can show that from a winning state, we we have a move which always takes us to the losing state, then we can be sure of a victory. So suppose a current state is winning, so this is greater than 0. And now we need to show that there exists a move always that such that we can go from this state, change some ai to j for j is less than ai, and then the XOR of these numbers will be 0. So did everyone get this part, or on how we have to show that we have to go from a non-zero state to a zero state? So if I am going too fast, you can tell me. Okay, so I assume everyone understood. So now we will look at this XOR value of AI A1 to AN. So let the XOR be some number. We will see the highest bit set in the XOR. So say J is the highest bit set in the XOR, 2 to the power J is set. Now if the XOR is 1, the Jth bit in the XOR is 1, there must be at least one number which has the Jth bit on. So if there no numbers had the Jth bit on, the XOR would be 0 in the Jth bit. So there must be at least one number with the Jth bit on. So let it be AI. So suppose it's some number. Say this is the jth bit. This can be anything. These are all zeros. Like bits higher than j are all zero. So now if we have the XOR value equal to x, we need to go from a state with value x to a state with value 0. Since in that case the other player goes to a losing state and it's fine for us. So suppose the XOR is x, and notice that x has bit set only in this. So now what happened? What will happen is if AI is this, we need to change it to a smaller value. So we will flip this bit, and now the thing is We have freedom to choose any bits here, freedom to choose any bits. So this number will always be, say this is, let's call it C now. So if the number C is less than AI, because the jth bit is different, these were all zero, so these will obviously all be zero. Now we have freedom to choose whatever number we want here, and we need to choose it in such a way such that AI, XOR C, wait, I will just write it, X XOR AI XOR C equal to 0. So C equal to X XOR AI. This is the same thing, because if this XOR is and XOR of this is 0, these numbers are same. So C equal to X XOR AI. And now if we take this number, notice that C will always be less than AI and will be non-zero. This bit will flip to 0, and these bits will change to some other values. These are 0, so these will also be 0. And the C or the XOR value X also has these 0. So say X is here, it has this as 1, and this can be anything. So did you all get this part, the construction? Hello? Okay. So this basically concludes the problem, since we can always go, if XOR is greater than 0, go to a 0 state. Choose, we can choose to go. And if XOR equal to 0, then always XOR is greater than 0 state. And notice that the last state where everything is 0 has XOR 0. So this is a losing state. So did everyone get the entire NIM problem? So this is the entire problem. This is the solution of finding whether Alice or Bob has a winning strategy. So now I will go over a slightly different problem. Suppose you are given a graph. It's a graph without any cycle and a directed graph. So say this is a graph. It's a directed graph without cycle. Directed acyclic graph. And each node represents the state of a game. And so if you are at X and there's a edge from X to Y, you can go from state X to state Y. If a node has no outgoing edges, so it's, if it's isolated, it's a losing state. And you need to basically find a winning strategy. And now the problem is that you are given not one graph but multiple graphs. In each move, you can choose one vertex in any graph and can go to a vertex leading outside of it, and so on. If you don't have any moves, that means all the vertices have out degree 0, you lose. So did everyone get this problem? So you are, no, it's not necessarily connected. It's a directed acyclic graph. So that means that there are no cycles in the graph, and so the game must always end. And also, like, if a vertex has 0 out degree, it's a losing state. You can't do anything after that. If it has a vertex, so you can go from here to here. So A, then you can go to B. So did you get it now? There are multiple graphs, and in there are many graphs, and in each move you have to choose one vertex out of all the graphs. So you can't choose multiple vertices in one move, only one vertex out of all the graph, and do the move. So did you get it now? So there is a, in each graph there is a token. You can assume that there's a token on a vertex. So there's one token in the entire graph for each graph, and you can move the token to another edge, to like another vertex, from a edge leading outside of that vertex. So we'll just illustrate it. Yes, yes, we are given the starting positions, and you have to tell if it's a losing state for the first player or the second player, like which player has a winning strategy. So suppose there's a coin here, we can just assume a coin, and we can go, say A to B there's an edge, so we can just, now A does not have a token, B has a token. And notice that you cannot return to A since there's no cycle. So if a player loses, if we look at the okay, I will just draw multiple graphs. Suppose this is a token in one graph, another graph, and suppose that no vertex has any outgoing edge, it loses. So suppose this one has an outgoing edge and this one has an outgoing edge. So now suppose these are the three graphs, one is edgeless and the other two have one edge. So in this case the first player can just move it here, the second player can move it here, and now there are no moves for the first player. Yes. So now this is for a token, but you can represent many games using a graph and use a similar analogy. So I will now explain the concept of Grundy numbers. So if a state is a losing state, it has value 0. So if a vertex has its out degree, so let the vertex be V and let the Grundy number be G of V. So G of V is 0 if vertex V has its out degree equal to 0. And now for the other vertices, this is how we calculate the Grundy value. So Grundy value GV equal to, so let the vertex V lead to say k nodes, B1, B2 and so on till Bk. So this will be the max of, I will explain what max is. B1, B2, not B1, B2, G of B1, G of B2, G of B3 and so on till G of Bk. So now we take the values of G of all the vertices leading outside of that vertex, leading out of that vertex, and we take the max value. I will tell what the max value is. Max is the minimum excluded non-zero integer in a set. So suppose a set has numbers, say a1, a2, and so on till am, and all numbers are at least 0. So it's the smallest number greater than 0 or equal to not in the set. So a set with 0, 1, 3, 5 will have max 2. Since 0 and 1 are there, 2 is not there. So 2 is the max. So did everyone get the definition of max? Yes. We are only dealing with sets with integers. And we are seeing the smallest non-negative integer not in the set. So now we will calculate the Grundy value of V as the max of all the Grundy values of the vertices leading outside of it. I'll just show an example on a graph. This is just a random graph. So this one has a Grundy value of 0 because this is a losing state, no edges leading outside of it, out degree 0. So now for this, it has exactly one leading outside of it, one edge. So it will be max of 0, which is 1. Now this one will have max of 0 and 1. So it leads to 1 and 0. So it will be max 0 1 equal to 2. Now, so this one leads only to 2, so the max will be 0. This one leads only to 0, so the max is 1. So did everyone get this part? The graph does not have any cycle, so we can always calculate these values. Okay. So now one important thing to notice, if you are at a vertex with Grundy value x, then you can always go, say x is greater than 0, you can always go to a vertex with g equal to y for any y less than x. So this is the max of all the Grundy values leading outside of that node. So you must have 0, 1 and so on till x minus 1 on the Grundy value. So since this was 2, you must have 0 and 1 leading edges leading to 0 and 1. So you can choose which one you want to go to. Is this part clear to everyone? Okay. And now, unlike in NIM, one key difference is that you can also go to a value higher than x. So you can go to a value z with z greater than x. But I will tell how to deal with this later. Now, the most important claim is, so suppose the we see the Grundy values in each graph separately. So you are given, say, multiple graphs. These are just rough drawings without directions. So say this is a graph, and you see the Grundy value of the starting nodes. So since this is S1, S2 and so on till Sk, you see the Grundy value of this, Grundy value of this and Grundy value of this. You take the XOR, and now I claim that this is equivalent to the NIM game. I will prove it. So you take the XOR of G of S1, G of S2 and so on till G of Sk. And now if XOR is 0, it's a losing state for the first player, else it's a winning state. So now notice that if we could go only to smaller values, it's the exactly same problem. So if we can go from x to any value less than x only, and notice that we can't go from x to x. Since it's a minimum excluded function, x is not there in the set. So we can't go from x to x. We can go from x to 0, 1, x minus 1. Suppose in the graph there are no edges with x to z. These are the Grundy values with x less than z. Then if this condition is not there, then this is equivalent to the NIM game. So did everyone get this part on how it's equivalent to the NIM game? Okay, so if you are in a graph, you are at a value x, you can always go to 0 in one move. You can always go to 0, 1 and so on till x minus 1. You cannot go to x. Did you get this part? So now it's equivalent to the NIM game, since you always decrease some number, some non-zero number you decrease, and you go to a smaller state. If it's all zeros, you lose. So it's exactly same as the NIM game if this condition is not there, this particular condition, that you cannot go to a higher state. So I will tell how to deal with this condition. But did everyone get the part on how we can just take the XOR of the Grundy values of all the starting vertices and determine who wins the game? Like if you have any doubts, you can ask. Okay. So now the important condition we have to deal with is, if a vertex has a Grundy value equal to x and say this has a edge leading to vertex 2, say this is v1, and with Grundy value equal to z here, and z is greater than x. And now this is not equivalent to the name game, since you can go to a greater number of you can go to a pile with greater number of coins if you make it equivalent to a name game, but that's not possible. So let's see how to deal with this. So now suppose that in our original claim, this is a winning position. The current set of starting positions is a winning position. If that is the case, the winning player should not deviate from the original strategy and just do as it is. So now we assume that the current player is the losing player, and it goes from x to z with z greater than x. And now what will happen is z always points to 0, 1, and so on till z minus 1. And now x is less than c, so x is there in this set. So the winning player, so the losing player goes from x to z. The winning player can just go from z to x and cancel the updates given by the other player. If there is no violation and the losing player goes to a smaller state, the winning player just continues in original strategy. So did you get this part where we can just cancel the moves not satisfying z is less than equal to x? The winning player can cancel it by just going back to the same number. Okay. Yes, there are no cycles, so this game will definitely end after some time. And now, no, now the interesting thing is that these don't have to be coins. Like you can ignore the coin game, and like any game with a finite states and no cycles. So any game can be represented as a bunch of states. So you can go from S1 state 1 to S2 and so on. You can calculate the Grundy values in the graph, and and if there are multiple games, you can just take the make like XOR of all the Grundy values. If there's just one game, you can just check if the value is non-zero. So is this part clear to everyone? Like the entire problem with multiple graphs and tokens. Okay, so I will now move on to the next problem. This is not related to Grundy numbers. Let's just open it. So I will just describe the problem. So you are given a polygon of convex polygon or insided convex polygon. Insides and convex. Like convexity is important here in this problem. And now what you do is there are two players again, and they take turns. So now if n is greater than 3, what they will do is they will select a vertex and its adjacent edges and take the triangle formed by them. So if they select this vertex, this is the edge, and they take the triangle formed by it, and they will delete it from the graph and say the area of this triangle is x. They will add x to their score. So score A, player A, and score B. So they will, if player A is making a move, he will add X. So now suppose player B chooses this triangle. After this one is deleted, so this is also a valid triangle, and this adds Y. The goal of the player is to uh, have the score less than equal to half of the area of the polygon. So A is area. So you take a vertex, you take its two adjacent edges. So this one, you take the triangle determined by them. So this one, and you just delete that. It's same as deleting a vertex actually. So you take the area as x and you add it to your score. So, and you delete the triangle, and now you get a shorter polygon. But I will just take a different color. So now this is deleted, and you just add the score of this triangle, area of this triangle to your score. And now the goal is to have your score score less than equal to a by 2. A is the area of the entire polygon. So now notice at the end, at least one player will have score less than equal to a by 2 since there are only two players. And if both have more than a by 2, it's a contradiction. So did everyone get the problem? And so now what you need to do is you need to tell which of you can choose one player. You can either play as the first player or the second player. You have to choose a way in which you can guarantee this. You can need to guarantee that your score is at most a by 2. You can choose whether you want to play first or second. And so also it's possible that both the players have the same score, which is exactly half the area, and that's fine. In that case, also you win only. Both the players win. So now you need to find a winning strategy for this, for the polygon. So like I can give you a few minutes to think. Also, this there's a code forces problem. This is the code forces problem. I just told you the statement. You can also have a link I have shared on Discord. Okay, so I have shared the problem link on the Discord, and you can have a look at it. Like if you want to submit your solution after the class and you want to code it. So now I will give a hint that there's a greedy solution to this. What? Can you repeat? Hello, can you repeat? You were asking something. So that is actually a good idea. And so now, using that algorithm, can you tell which player will win? So that's actually used in the solution. I will also explain the proof. But you need to tell, like in even in the greedy algorithm, which player will win. Will the first player win or the second player win? Uh, Okay, so it depends on n also. There are n minus 2 moves in the game total. So once there are only two vertices left, the area is 0 and you leave it. So now it's possible that there are three moves and the first player, second and third. So the first player will have to do two moves and the second will have to do only one move. And it's easily possible to come up with a counter example where the first player loses. Yes. But now you need to prove one more thing. I will now explain for n even. So if n even, first player wins. But we also need to prove. So now if we suppose that we prove that we can't take always the small, it's possible that there's a triangle, say, which does not use two consecutive edges but is smaller than this. We need to prove that such a scenario does not happen. So we need to prove that given a n-sided convex polygon, there is a triangle with the smallest area which uses two consecutive edges. And so like if a triangle does not use any two consecutive edges, then it like there must exist a triangle which uses two consecutive edges with minimal area. Same area is fine, but we want minimal area. Like if there are two triangles with same area, but we need to guarantee that the smallest triangle here has two consecutive edges. And now notice that if we remove this, all the remaining triangles which will be chosen in later moves will have area at least this. We need to show that. I will now explain the proof. So now suppose a triangle, the smallest triangle, the triangle with the smallest area does not use two consecutive edges. This means that there must be a vertex C such that, let it be ABC, such that there is a vertex between C and A and a vertex between C and B. They can be multiple, say two here, one here. And now we need to show that this is not the smallest triangle. I will now show that. So now let the neighboring two be X and Y. So CAB is the triangle and X is between A and C and Y is between C and B. This must exist, else they are two consecutive ones. There must be a vertex C such that, like, of course it's possible that it's not C but A or B. So you can just rotate the triangle in that case. So now notice that area of a triangle equal to base into height by 2. Now base is fixed, say A and B. So this is constant. And now we need to show that at least one of X and Y is less than the smaller height. So we will denote it by small letters. So now claim min X comma Y is less than C. So now I will explain why this is true. Suppose the opposite, that X and Y are both at least C. So this means the height is here is at least this. The height here is also at least this. And now notice that a convex polygon requires you to have every angle less than 180. And so if these two vertices are above, this will be a concave polygon. This angle will be more than 180 or equal to 180 in this case. So did everyone get this part on how we can go to a smaller height triangle? One of X or Y must be less than C. Yes. So now we have showed that the triangle with minimal area must have two consecutive edges. So say these are two consecutive edges it has. I just use a separate color. So this is the smallest. It's not the actual smallest in this diagram, but we are assuming it to be, like, the diagram is not drawn to scale. And we just delete it. Now, so if n is even, we just delete the smallest triangle every time. We are the first player and we delete the smallest triangle every time. And now if we take the areas of the triangle deleted it in each move, so say n minus 2. And then notice that a1 is less than equal to a2, a3 is less than equal to a4, a5 is less than equal to a6. We do the odd number of moves since we are the first player. And we always choose the smallest triangle, and there are no triangles with length area more than that. We always have this condition. And so sum of our values n minus 2 is even. Sum of our values is less than equal to a by 2. So is the part clear why the first player always wins when n is even? And now if n is odd, we can use a very similar argument. If n is odd, the second player always has a winning strategy. So note, assume that the first player does any random move. Say it deletes. Wait, I'll just draw a new diagram. Let's say it's a pentagon, and the first player just deletes any random triangle. And now notice that now we have n or even, and we can play the game such that score is less than equal to a dash by 2. A dash is the area of the remaining polygon after the first move, and A is original area. And this is less than equal to a by 2. So the second player always wins. The first player can do anything randomly at the beginning and it does not matter. So is this part clear? Okay. So I can do one more problem. So now you are given three undirected graphs with some edges, like three different graphs, and you will build a graph with n cube edges such that you in each n cube way, like, you take one vertex from each. So I comma j comma k pairs, which represents vertices xi, yj, and zk. And now we will span edges in W as follows. For each edge in X, like in the first graph, we will span an edge between, like if the edges between XU and XV, we will span it between XU Y comma Z and XV Y comma Z for all Y and Z. So did you get this part? Like you all can read the problem. So basically, this is similar to our game where we had three like we had three graphs and we have a token on each one, and in each move we can go to a vertex greater than that. Uh, that's a huge hint actually. So I encourage you to read this line. So these are the vertices xi, yi, and zi. So did everyone get the problem statement, like the graph, how we span the edges in the graph with nq vertices? And now we let the weight of a vertex xi, yj, zk to be equal to 10 to the power 18 into I plus j plus k. So x1, y1, and z1 will have the least value. These are undirected graphs, by the way. These are not directed. You have to find the maximum possible total weight of the vertices in an independent set in W, and you need to print that total weight modulo something. So you need to find the n cube algorithm to find, and not n cube for this but I would encourage you to try to find the n cube solution first to find the maximum total weight of the vertices in the independent set in W. And now notice that finding independent set, maximum weighted independent set in a general graph is NP hard. So you need to find a fast solution and you need to exploit the properties of the specific graph. No, you define edges in W as follows, as the mentioned here, and you find the independent set in W. So now, wait, I will just explain. So say we have a state x1, yi, zj, ij are random, can be anything. And we have x2, yi, zj. If these two are same and these two are connected in the first graph, then there's an edge between this tuple and this tuple. So there's an edge between two tuples if two numbers are same and one number is different. It can be the first number or can be the second number also, and these are connected in say the second graph. So if the second numbers are different, must be connected in the second graph with other two being same. Or we can maybe have the last two numbers same and the first numbers connected in the first graph. So did you get the graph edges in the graph? So you need to find the minimum independent set in this graph. The weights are defined as 10 to the power 18 I plus j plus k for a tuple xi, yi, j, zk. So I'll give you a few minutes to try the problem. So now I will tell a greedy strategy. This is a relatively simple strategy which is not extendable directly, but you will need to come up with a way such that it can be extended to n is 1 e5. So you can find maybe a solution less complexity than n cube. N square also, it won't work for this, but if you can find with any solution less than equal to n square, it's fine. Okay. No, I will tell the greedy brute force solution. In the brute force solution, notice that the weights are 10 to the power 18 I plus j plus k. And if I plus j says c, and we take all the vertices with I plus j plus k less than c, the value here will be greater than sum of values here. So this is because 10 to the power 18, we multiply every time for each increase in the sum, and the vertices are at most 10 to the power 5. So it's always optimal to take a vertex with bigger weight than all the vertices with smaller weight than that. Did everyone get this part? So now another observation is, if two vertices have the same sum I plus j plus k, then there cannot be an edge between them. I will show why that is true. So if I plus j plus k equal to c, say I1, j1, k1, and I2 plus j2 plus k2 is also equal to c. Either they are all same, so they are the same vertex, or one is lesser and one is more. So in either case, there cannot be exactly one different number. For the edge to exist, we need exactly one different number and two same. So the sum is different. The sum cannot be, there cannot be an edge between two vertices with the same sum. So is that part clear? So now what we do is, we can do a greedy strategy. We sort the vertices by their weight in descending order. We sort the vertices by weight in descending order. And we take a vertex if there's no neighbor of it which is already taken. So if a vertex has a neighbor, say with a value higher than that, say this is value c, this is value d. Now if d is already taken, then we don't take c. But if a vertex leads to only to vertices which are not taken, we can take it, or it has out degree 0. So we take the independent set greedily. So is this part clear? And now this solution will be n cube, unfortunately n cube. And now we need to find a faster solution to this. So now notice that what are we doing? We assign a state 1 comma 0, 1 if we take, and 0 if we don't take. I will now show the main thing in this problem, which is very nice. It's one of the nicest problem I've ever seen. So now, if a vertex leads to say k vertices and all are 0, then we take it. But if this leads to some vertices where at least one is 1, say others can be 0 also, that's irrelevant. If we have at least one, we won't take it, since we already have a higher weighted vertex and we cannot take that. So now, the main observation, like, do you all want to try, or like, should I tell the solution? The greedy approach works, but it's n cube. So you have a n cube solution and you need to have much faster solution. So now notice that from we take a number only if its neighbors with value greater than it are not taken. All the neighbors are not taken. If we have either one taken, we can't take it, since then it won't be an independent set. So do you all want to try the problem more, or should I go to the solution? Okay. So now I will give a hint. So now suppose that this we now like instead of an independent set, we view the entire graph as a game, and notice that if we consider one as losing here, notice that from losing we can only go to winning if zeros are winning, but from a winning state we can always go to a losing state. So this is a losing state, and from a losing we are forced to go to a winning state, and for a winning state we are forced to, we can choose to go to a losing state. We can always have a choice for the other player to lose. And so now the problem reduces to find sum of values of all losing states. So did you get this part? Did you all get this part? So we define each vertex in the graph as a losing state or a winning state in our original game, where we always have to go to an outgoing edge, through an outgoing edge, or if we don't have any moves we lose. So now notice that we can always go from a winning to a losing, and losing we are forced to go to a winning. Okay. And now let's see what the original graph is like. Each vertex is denoted by a tuple I comma j comma k, and from an I like we can change exactly one in one move. We can go to a vertex which is connected in the original graph. So now instead of having a tuple we can just have three individual graphs, and also we only go to higher vertices in this. We are, it's unlike the undirected graph given in the problem, we only go to the higher vertices since we are discussing the vertices in the decreasing value. So I plus j plus k we sort in descending order. So now if we are at a j in the say the second graph, we can go to a higher value k with k greater than j in the second graph. And so now this reduces to our original problem. Given multiple graphs with a token on each one of them, you can do a move and you can go to a uh, You can change exactly one token in one move, and if you cannot move, you lose. So now we need to like find the sum of values of all losing states. So suppose I, j, and k. So did you all get this part? So now, yes, yes. So like if you want to check after the class again, you can write the recurrence of the greedy algorithm and the graph winning and losing state in W with this, and you will find that it is exactly same. So now we learned the Grundy values just now. We calculate the Grundy values of GI, GJ, and GK. We take the XOR. If the XOR equal to 0, this is a losing state. We just need to find the sum of the values of all the losing states. So GI, XOR GJ, XOR GK is equal to 0. And now we can remove the GK here and put it to the right hand side. We need to find the sum of the values. So for all vertices of this form, where the Grundy values, we can also calculate the Grundy values in linear time. Notice that we can calculate them in n log n, maybe you can easily do to calculate the max. You can just find the Grundy values in the original graph, all the three graphs. So these are all bounded by 1e5. If m is the number of edges, you can do it in m log n. You can also do it in linear time if you want to, but it's not required. So now the value is 10 to the power I plus j plus k. So now I will show a very interesting observation. Suppose we have a graph with m edges, and now notice if that a vertex has k outgoing edges, vertex v has k outgoing edges, 1 to k, then Grundy value of v is bounded by k. If it's more than k, there must be at least k plus 1 outgoing edges, since 0 to k must be there. So Grundy value of v is bounded by k. And now so Grundy value of vertex 1 plus Grundy value of vertex 2 and so on is less than equal to m. It's a directed graph. So the sum of the Grundy values is at most m. So did you all get this part? And now we will look at the number of distinct Grundy values. So now we have at most 2 to the power. So suppose that all the values are distinct. Hello. Okay, and I will just show it. I will show that the number of distinct Grundy values is at most 2 root m. Like if we can show that. So suppose that we want the maximum number of distinct numbers, say 1 to x, and the summation, so basically x into x plus 1 by 2 is also less than equal to, has to be less than equal to m. If we have at least x distinct numbers, say we have at least x plus 1 distinct numbers, say 0 also, then the sum is at least x into x plus 1 by 2 if we have at least x plus 1 distinct numbers, and this has to be less than equal to m. So we get x into x plus 1 is less than equal to m. So x square is less than equal to 2m, and x is less than equal to actually 2m square root. So the number of distinct values is very small. And now we get to the original problem. So gi XOR gj equal to gk are the losing states. I is of the first graph, j is of the second graph, and k is of the third graph. So we need to find the sum of 10 to the power I plus j plus k multiplied by 18. The summation overall in like very less time. We can't do n cube. We can do n root n, or we can do n ln log n, and so on. So now notice that the number of distinct values is very less. It's now not bounded by m but by 2 root m. So all are less than equal to 2 root m. You can try for a minute on how you can compute efficiently in m root m. Okay, so now we need to find for all values which satisfy this. We can just brute force over all possible distinct Grundy values. So say this is root 2m at most. This is also root 2m. This is root 2m, and if we multiply them, we get m root 8m. So 2 comes outside, so 2m root 2m. So it's order m root m to iterate over all the triples such that we choose exactly one from each. And now notice that 10 to the power 18i plus j plus k equal to 10 to the power 18i into 10 to the power 18j into 10 to the power 18k. So now what you do is, for a fixed Grundy value, you calculate 10 to the power sum of 10 to the power 18i. We'll just show it here. So in the first graph, you see all the numbers with Grundy values, say a fixed x, gi1, gi2 equal to x. Suppose you have multiple vertices with value x. You calculate summation of 18, 10 to the power 18, I, I star. So basically you can iterate star from 1 to how many numbers are there. So now for this particular value, we just take the value for a fixed Grundy value in the first graph and multiply it by second and third. So now if we say have 18 I1 plus 18 I2, so 10 to the power 18 I2, sorry, plus 10 to the power 18 I3. We multiply it by 10 to the power 18 J1 plus 10 to the power 18 J2, say, and so on. We can fill more. And if we look at each term operate like found in the expansion, it will be of the form 10 to the power 18 I plus j plus k. Let this be whatever. So did you all get this part? Like each term in this expansion will be 10 to the power I plus j plus k into 18. So the Grundy values, we want the XOR of the three Grundy values to be 0 for it to be a losing state, right? So now the Grundy values in each graph are, the number of distinct Grundy values is at most 2 root m. Yes, we can just brute force over all the triples. So it will be order m root m. Okay, so that's it for today. Thank you everyone for attending the lecture.